To the first instalment of the Ihaka lecture series for 2019. My name is Atakohu Middleton, and I'm a communications advisor to the Department of Statistics. Now, in this role, I've written quite a lot of stories about the man who helped turn a single letter, R, into a runaway global success, and there's a few things I've learned over those years that I'd like to share with you. So Ross's heritage is Ngāti Kahungunu ki Wairarapa, Rangitane, and Pākehā. For Māori, he's a very important and rare role model in a field where we have too few Māori academics and Māori students. Now, to trace the roots of Ross's success, we need to go back in time to his paternal great-grandfather, Piripi Ihaka. Piripi was born in 1861 in Papawai, Wairarapa, and married an Englishwoman, Mildred Baker. They raised their family near Masterton. Piripi believed in education, and his grandson, Ross's father, was one of the first from his area to go to high school. Apparently Ross's father was told, and I quote, "You learn everything those Pākehā have got to teach you or I'll kick your ass," end quote. Now Ross, who many of you will know has quite a dry sense of humour, will tell you that it's a sentiment he really likes to pass on to others. So, Ross's father Jack was one of the first from his area to go to high school, and he became a teacher. Ross's mum Edna was also a teacher, and Ross earned a PhD. As he once told me, these are quite big steps in just 2 generations. So at this point, I'd like to acknowledge Ross's ancestors, both Māori and Pākehā, on whose shoulders he stands, and Ross himself, who's hiding in the second row. E ngā tūpuna, nā koutou tēnei te maiti, i aki, i hotohoti tana whai mātauranga. Rātou ki rātou te hunga mate, tātou ki a tātou te hunga ora. Ross, e te manukura, mō tuku tō taonga koreheri ki te ao, ko te whai o te māramatanga, te take. Ko tāu e whakatinana hea pēnei ti ana. E hara taku toa i te toa takitahi, engari he toa takitini. Anea mihi kāreri ki a koe. Now that roughly translates as, those who have gone before you encouraged your child's pursuit of education. Ross, you gifted your child. The legacy you inherited and what you have passed on is perhaps our Māori. Success is not the work of one, but the work of many. We can also apply this idea to R itself. Ross and his co-founder Robert Gentleman got things going, but we have many others to thank for what R has become over the years. So now I'd like to hand over to Associate Professor Jan Lindsay from the Faculty of Science. Thank you.
Thank you. Kia ora koutou, ko Jan Lindsay taku ingoa. I'm an Associate Professor in the School of Environment and the Associate Dean Research in the Faculty of Science, and it gives me great pleasure to welcome you all here this evening to the 3rd instalment of the Ihaka lecture series, named, as Ata mentioned, in honour of Ross Ihaka. The Ihaka lectures aim to address issues and discuss topics of public interest around the interface between the disciplines of statistics and computer science. The theme for this year's series is machine learning. The field of machine learning, although inherently statistical in nature, has for quite some time found a home in computer science and engineering departments. As a consequence of this, it has developed a rather distinct identity with a language and a sometimes distinctly non-statistical nature of its own. Recently, the public has become more aware of this field, partly as a result of 2 developments. Firstly, advances made in neural networks and in computational Bayesian statistics have led to a flurry of projects and products that the public can at least superficially understand. An example from our own field of volcanology was described in an article published last December in the journal Science, entitled "Artificial Intelligence Helps Predict Volcanic Eruptions." The idea here is that new algorithms have been developed to automatically process the vast array of satellite information in volcanic areas to detect ground movement that might indicate magma coming up to the surface. The second development is the rise of news stories news stories where black box algorithms have led to negative outcomes. A good example of this can be seen in an article just last month in the UK newspaper The Guardian, entitled UK Police Use of Computer Programs to Predict Crime Sparks Discrimination Warning. It's easy to see why the use of algorithms for policing to predict, for example, which citizens are likely to reoffend, raises ethical questions around the collection and use of data in this way. This year's Ihaka lecture series addresses different aspects of machine learning, ranging from implementation to ethics. And we have 4 fantastic speakers over the next 4 weeks, and we hope you enjoyed tonight's speaker and that you will join us for the remaining 3 lectures after this. So I'll now hand you over to Yong Wang to introduce the speaker.
Thank you. My name is Yong Wang. I'm a senior lecturer at the Department of Statistics. It's my great pleasure to introduce our speaker tonight, Professor Bernhard Pfahringer. He is a professor with the Computer Science Department at the University of Waikato, and he was the head of department of the computer science just a couple of years ago at Waikato. And his area of expertise is in machine learning and computer data mining. And he has published a book and added 3 more books and published more than 30 journal articles and more than 100 conference articles. He is one of the major team players in the internationally well-known Wakeup project. I suppose you have heard of that. And he's also the main writer of the online data mining suite software called MOA, M-O-A, Massive Online Analysis. So, ladies and gentlemen, please join me in welcoming him for giving the lecture. Thank you.
Good evening, everybody, and thank you very much for this introduction. Thank you for reminding me how old I already are, because achievements just accumulate over time, and if you're older, you have more of it. Very easy. And let's start with. So, a very quick overview. What we're going to do today is I want to quickly add a little bit more in terms of introduction, so that you have a better idea of my background, where I'm coming from. I'm going to talk just briefly about COSI, which is our Center for Open Source. I'll talk about 3 major systems: Weka, Adams, and MOA. Sure. Yeah. So we need 2 microphones, one for the room and one for the recording. Which is great. Okay, so very briefly about 3 systems and then a little bit about future outlook and stuff like that. But before I do that, I want to say it's a really big honor to be invited here. And it's a little bit intimidating, and I've got to be very careful today because, as you heard already, I'm a computer scientist. And we sometimes have a weird approach to machine learning. We're like the cowboys somehow. We train models first and ask questions later. Which, of course, in your stats lectures, you're always being told to look at the data carefully and visualize it. I agree with that, but sometimes we do it differently. So bear with me. And yeah. So originally, I'm from Austria, which you can see here, kind of far, far away from here, but has some similarities in a way. So this is, I really like the way you would traditionally introduce yourself in a Mari context. And I've tried to, just with 3 slides, do that quickly here. So basically, this is my mountain, Ko Notke te Temonga. This is where I grew up, where I learned to ski before I went to primary school, stuff like that. Pretty cool place. This is my river, Ko In Teava. Weird color is fed by glaciers, so you get these colors like Queenstown might be similar. And this is my tribe, Konati Tirol Teivi. If that reminds you of Oktoberfest, Munich is pretty close to Austria. And we share a lot of similarities, but also we love to hate each other. Like you and the Austrians get along very well, usually. And I'm more to the point, in 1984, I was lucky to be a summer student in CERN, which is the European Center for Nuclear Research. And that kind of was the defining point for me and my career. Because back then as a student, over that summer, I actually did some data mining without knowing that that field actually existed. So I was tasked there to basically look at lots of logs of what people use computers for and maybe find patterns that can then be automated to make the physicist's life a little bit easier. And one thing, if you are not aware of that, physicists are great to work for because they always somehow manage to get a lot of money and they produce a lot of data, and so they always have the latest hardware and the latest software to work with that. And so it was really amazing. It was a great summer. If you can ever do an internship in a cool place, go for it, definitely. Now, many years later, I'm a computer science professor at Waikato, so what I've done here is just basically take my homepage and some pages that link to that and to word cloud, and yeah, it's pretty obvious that I do machine learning and things related to that, and not much else, to be honest. It's a shame in a way, because a long time ago I had different interests as well, but there's only so much time in the day and life's finite, so you need to focus on the important things. And it's also the case that I'm not just a computer scientist, but also in machine learning you get different approaches nowadays. And it's not formalized like in physics, where you have theory and experimental and maybe applied. But if you look at what I generally do, you probably would say experimental machine learning. And so, yeah, I have a couple of students and too many things to do, but it's great to be invited to talks like that and then take some time and focus on this. Now, about the real content. One slide about our Center for Open Source Innovation. A long time ago, and I'm not really sure how it came about, but we basically decided that we want to do our stuff as open source for a number of reasons. And it was actually a bit of a fight with the university because the people did not really understand what that means and were not necessarily supportive of it, and were actually afraid that we would give away valuable stuff for free. Over the years now, they have learned that even with open source software, you can earn some money. And the university has made a little bit of money out of our work. So I think they're more happy now these days. Okay, so there's a lot of other interesting stuff happening in terms of open source at Waikato, like networking mainly. But in terms of machine learning software, we have the three main systems. And the most well-known one, and it's actually still used quite a lot around the world, often for teaching, is Weka, which is a machine learning workbench, and I have a few more slides about that. Then there's something that almost no one knows about, but I think is actually also quite cool, which is called Atoms, and I'll tell you about that in two more slides a little bit later. But then the main thing for today will be focusing on MOA, which is kind of the thing that I'm really passionate about. And there's a couple of other minor things that usually, whenever we have, especially PhD students, we try to make them turn whatever they did also into a software package that will be distributed. And sometimes we even can be generous and have some money to give them 3 or 6 months after finishing their PhD to actually clean everything up and make it nicely available. Okay, so Weka, the Waikato Environment for Knowledge Analysis. Like the other two systems, for whatever reason, I'll come back to that, we've chosen Java. And so everything is in Java. And these days, there's a lot of algorithms there. And you can do all the standard things you want to do in machine learning. You can use classification, you can do regression, you can do clustering. And I've put that in red there because these days it's important to have that. So you already heard that a few years ago, machine learning became really popular also for the public. And this was mainly the success of deep learning, the third wave of neural networks. And Java is not necessarily the best vehicle to do deep learning. But over the last few years, some people in the US have developed this deep learning for Java library. And last year we had a very good German student that we employed for almost a year to basically take that library and integrate it into Weka so that you can now use that deep learning library and of course that accesses graphic cards, so it's really fast, in a Weka way. To be honest, personally, my deep learning experiments, I usually use Keras for that, or maybe FastAI. Because this deep learning for J is a little bit limited, unfortunately, because they support all the regular stuff, but if you want to have something more fancy or newish, they always lag behind a little bit. So yeah, there's a caveat there. But if you want to use something which is pure Java, but still can access a GPU, and is inside the Weka platform, then this is what you want to use. And there's this other, maybe not so frequently needed application areas, and they're all supported. Now the interesting thing about, one of the interesting things about Weka is that it has a GUI, and not just one, but 3, and I will have 3 slides for that. But of course, like any Java code, you can also use that as a library in your own code. And because it's open source, well, there's some complications because we usually use the GNU public license, which means if you integrate it into your code automatically also has to be open source. And that's a deliberate decision that we've taken. Even though for more, you can also get Apache licensed version. So it's not necessarily a condition that will stop you from using things. Or we have a command line interface. And personally, I use the command line a lot because I often want to run something on a server, and it's very easy to SSH into a server and just have a few command line things going, and you don't need to worry about big GUIs and transmission times and whatever. Now, Weka has been around for a while, and so it's kind of reasonably mature and also now supports interaction with a lot of other systems. And of course, most importantly for you, for this audience here, R, which we already heard about. I mean, I think it's still kind of amazing that things like R and Weka both come out of New Zealand, a little country, and basically are being used around the world by many, many people. I think it's really quite an achievement that New Zealanders should be proud of. So we have interfaces to R, to Python, to MATLAB, and then there's these systems like KNIME and RapidMiner, where RapidMiner actually started as another GUI around Weka in Germany. And after a while, those guys started a company, pretty successful now. They've moved to the US. They're a reasonably large company that does consulting. And actually, the RapidMiner product has developed a lot. And I think in the free version, you can still use Weka as a little plug-in part. There's a lot around that. And KNIME is kind of similar to RapidMiner, also coming out of Europe. In this case, actually Switzerland. And I think they're probably one of the most successful current small consulting companies that does machine learning that way. Because there's this end with the small companies, and then now, like the last few years, you have the large companies, Google and Microsoft and IBM. They're all offering various types of services, some of them for free, mostly in the cloud. And also Amazon is there, of course, as well. Okay, so quickly, very quickly, the 3 GUIs in Weka. So the idea is, you want to actually look at the data before you do something, so we force you to load the data in this first part of the GUI. You may notice that we have actually got 6 different tabs, and currently we've selected a Preprocessing tab. And someone has loaded a very tiny little data set that will be familiar to everyone who's done a statistics course. It's called the iris data set, which is just about 50 examples from 3 different types of flowers. And you get a little bit of visualization here. So you see there's 3 classes, and you see how for that attribute that has been selected, the classes distribute in terms of values. So like the dark blue, the low values are only associated with dark blue, and the highest values are only associated with light blue. And in the middle, there's like, yeah, can be anything, but with different probabilities or frequencies. And once you've done that, you could switch to the Classify tab and run a lot of classifiers and collect results, get an idea of what works, what doesn't work. You could use clustering, you could do association rules. And there's actually a visualization tab. But to be honest, the visualization is quite limited. So if you look at packages that you get with R or with Python, they're much more powerful. But as I said, if you wanted to, because of the interfaces that we have, you could go out and use some fancy, like Seaborn, Python plot, or whatever. Now the next GUI is much more graphical. This is this idea of having like a graphical programming interface where you have gadgets that you plug together with connections. So it's usually a 2D canvas, and you have all types of gadgets for the various different bits that you need, and then you have some kind of data flow. And in the simplest case, this is just one flow, but there might be, it might split up, it might merge again. So this is very useful for beginners, but it doesn't scale that well, because we need a lot of real estate on the screen to do a few small things. And we'll see a little bit later that there are alternatives to that. But for absolute beginners, GUIs are generally a good idea. And also GUIs are useful if you have a lot of options. And if you don't regularly use something, you will not know about all the options. You will not remember what they are and what reasonable ranges for values are and so on and so forth. So there is something to be said in terms of GUIs. But on the other hand, once you're a bit more of an expert or like really focusing on a little bit, sometimes the GUIs just get in your way and are too slow. Now this is the third GUI, and that's actually really interesting for one reason. There was maybe 15, 17 years ago invented in its first version. The idea is that this allows you to set up an experiment where you have one or more data sets and one or more algorithms, and you run all the algorithms across all the data sets, and you collect all those results in a reasonable way. So usually it's some form of cross-validation, or maybe even multiple cross-validation runs. So the default here is actually 10 times 10-fold cross-validation. And then you can compute a lot of statistics from that, and you can view that, you can plot that, but most importantly, that tool has a feature that allows you to generate a LaTeX table out of the results. And that kind of had an interesting normative effect, because there was a number of years when you went to a conference and you looked at people's papers, you could immediately tell they were using Weka because they used the table in the format that you're familiar with. They had used this experimenter to generate the results. Of course, what it also means is it's a lot of responsibility, because if you think about if we have a bug in there that computes the significance the wrong way, then that invalidates a lot of published research. So this is probably one bit of code that has been looked at quite a bit, just to be sure that it actually is doing what it's supposed and what it's advertised to do. Okay, maybe just a little kind of history of Weka to give you an idea that things may take a long time, but may still be good. So Weka was actually started by Ian Whitten, who is almost retired. He's officially retired, but on a kind of, I don't know, currently maybe a 20 or 50% contract, and he's slowly kind of cutting that percentage. But he's still keen to do a little bit of work. It was his main idea in the early 90s that when he came to Waikato, he wanted a tool for teaching. He wanted to be able to teach students in a hands-on way. And at that stage, most machine learning algorithms were written in languages like C or even Prolog or Lisp, but there were already people who made that stuff available for free. And so they collected all what they could get, and then we want a GUI, we want some interface. Back then there was TickleDK, if anyone ever heard about that. And they worked to some degree, but it is a nightmare maintaining something that is done in like 5 different languages. And so when Java became available, Ian had this idea that, well, mainly targeting teaching anyway, so at that stage Java was really slow, but there wasn't an issue because we wanted teaching. But it's portable, so it might be easier for people to actually run it on their Macs, on Linux, or on a Windows computer. And it really took off in 1997 after a summer student did like a proof of concept. It was mainly Aibe Frank first. He was one of Ian's PhD students who really kind of got into it and did a lot of initial development work. And then 2 other PhD students, Len Trick and Mark Hall. And so Aibe is still, now he's a professor with us. He stayed at the department since then. Len went to a company and is still doing machine learning consulting for through a local company in Hamilton, but a company that over the years also had some offices in the US and stuff like that. And Mark Hall is still doing machine learning consulting out of his home in Rotorua for international companies, mainly Hitachi these days. So that gives you kind of the design decision. So people sometimes complain that Weka is slow, and that's true really for some parts, not for everything. And it is true whenever you use the GUI. If you just use a command line, then it can be really fast. Now, in the 2000s, things changed a little bit because suddenly we had some money, and that's probably my main contribution to Weka. I mean, there's a little bit of source code in Weka that I've written and stuff like that, but some of the money supporting those people came through grants that I was able to get. So Richard Kirkby was also a PhD student of Jeff and mine, but his Weka work was before his PhD. And then Peter Reutemann, a German master student, he did a master's with us and then went back, and then we hired him as a research programmer, and he's still a research programmer doing consulting and using our tools and improving our tools every day. And what you see over the years is that things grow and grow and grow in terms of software. It's really bad, and then it's at a point where you either want to throw it away and start from scratch, or if you can't throw it away, you have to restructure it. And then in a language like Java with inheritance, you end up with these like really ugly hierarchies, and I've just given you one example here where you go from Java language object, abstract classifier, single classifier enhancer, the iterative single classifier enhancer, the parallel iterative single classifier enhancer, the randomizer, and so on and so forth. And this is because you only have single inheritance, and at that stage, interfaces did not allow for code. Nowadays, with the modern Java versions, you could do that very differently. And okay, this is not showing up there, so it's no problem. So it would be time to rewrite it, actually. But so far, no one is keen. Now, another interesting development was in 2006, I think, maybe 2007, I'm not 100% sure of that at the time. We got approached by this company, Pentaho, which was very interesting because it is was an American open source company. And after some talking, they actually managed to convince the university that we have a partnership where they get some exclusive license on Weka for some parts. Because even though Weka is GPL, as a company, you could still buy a commercial license. So sometimes people were buying literally just the decision tree code or stuff like that. And there was a little bit of bad blood from the computer science department because we were sidelined. It was really just the lawyers talking to each other, and we thought we should have more input, but it didn't really happen. But anyway, it all turned out well, and many years later, in 2017, Hitachi bought out Pentaho, and it turns out that the university had some equity in the contract. And so the university was actually getting some money suddenly out of the blue, and that meant that we also got some money through the university. So if you can get equity in something, go for it, because it might pay off. And it wasn't a lot of money, it was like a 4-digit sum for me, but it's nice to have. And equity can turn into money. It's nice to see that. Okay, now something totally different, ADAMS, which is the Advanced Data Mining and Machine Learning System, which is more or less not really a machine learning tool, but a workflow system, something that allows you to specify complex setups. And if you think about how you would do that, you would either do scripting, writing some code in some friendly language, or on the other hand, you would have this totally graphic knowledge flow interfaces. And this thing is somewhat in the middle. It is based on a tree structure, because for a lot of things, trees are good enough. Sometimes you need DAGs, directed acyclic graphs, and this is supported in some way, so you can do everything you want to do. But if you look at this thing here, on this kind of same amount of screen real estate, you can specify a lot more things than with the fully graphical GUI. And on the other hand, this is still something that people who don't program or hate programming still are happy to use and to do. And this is really Peter Reutemann's brainchild, and he's the main force behind it. And over the years, he's developed it into quite a big thing. And it's really powerful these days and supports a lot of things, also specialized stuff. So if you want to work with images and audio, so they do consulting for, say, chemical labs in the Netherlands, for instance. And these guys are having all kind of machines there that need analyzing of spectrograms or whatever, but they also then branched out and they now go to farmers with big glass houses and they put cameras in there and then they count bugs and stuff like that. And all that is done with basically beta software at the back end. And he always builds some extra tools if he doesn't like what's there in Weka. So, and now finally they also have some interested companies here in New Zealand as well, so it's not just the Netherlands anymore. That's kind of cool. Now, finally, we actually get to where I really want to go to, which is MOA. MOA is kind of dedicated to working on data streams. And I will show on the next slide why I think this is really important. And of course, the immediate question is, well, why didn't you just extend Weka? Why did you have to build a new system? And there's a couple of reasons, and I think most of them are good reasons. So it turns out that for what we want to do with streams, we need more flexibility than what Weka allows you. And we didn't want to extend Weka yet again and make it more complex than it already is. And so also a couple of design decisions that, like this tool was not targeting teaching. And so there are some things that you want to do differently. And also, as a computer scientist, you love to build stuff. And it's much nicer if you can be able to start from scratch. But didn't mean we forget everything about Weka. We built it in a way that's easily interoperable. Actually, originally it even shared some core classes, but that has changed now. And generally it's available on the GPL. And there's this name again, Richard Kirkby. So what he did for his PhD was kind of the first version of MOA. And after that, we were really lucky to get this really talented PhD student from Spain, or I should say Catalonia. He's particular about that. He finished his PhD there, but I was visiting us during his PhD, and then we hired him immediately as a postdoc for a number of years. I was lucky to get one of those Build IT grants or whatever they were called. It was really great. It was excellent. And that really kind of gave the research around MOA that we did a big boost, but also the software itself. And you see that he had an interesting career after that. So he went to Yahoo Research Labs back in Barcelona, then to Hong Kong to work for a Huawei research lab there, Noah's Ark, and then to Paris, worked as a professor at one of those like really highly ranked specialized universities. And there's the really good news. We have him back now. So about 1.5 months ago, he started with us as one of those entrepreneurial professors. You may have heard about the government program that supports that. So it's really great to have him back. Okay, so why MOA? This is why. If you look around yourself these days, you will see that there's a lot of activity that is digital and recorded. And if it's not digital yet, we are in the process of digitizing it. So for instance, even if you look at farms, they have a lot of sensors for milking, they're automating the milking, and the cows might have pedometers so they can see how far they walk around every day. Everything is digital now, it's collected, and you have these enormous amounts of data that come in continuously. And we need to be able to do something with that. And we want to be able to do something with that because there's always some bit of interesting information in there that can be handy. Now, the main issue with that is not just that it's a lot of data, but also that it violates all the assumptions that you have in standard machine learning. Because those streams, and so most of the world, is not IID. And I don't have to explain to you guys what IID means. But if you look at what standard machine learning does, you have a training set and you have a test set. You always assume that they come from the same distribution and they have been drawn in the same way. And in practice, this is not the case, or this is often not the case. There's all kinds of things why this is not the case, like all these phenomena we know from time series, like trends and seasonality, and things happen that are out of the ordinary. But even the sampling itself, like you collect information about patients in one hospital, and then this model doesn't work so well in another hospital because the patients there are different. So this happens all the time. And there was something that was mentioned earlier today, and I just want to just quickly mention that you may have heard about these issues with face detection or detecting pedestrians, that if you're a white male, and usually as a young white male, you're easily detected, but if you are dark and female, then it's a lot worse. And again, this is because the way they have trained the data, there were a lot of examples there from the class that works well, and weight not enough from the others, and therefore you get this problem. And it's very obvious to us. But a lot of the people who apply machine learning now, well, either they forgot about it or they have never been properly taught about it. Just a few examples of how am I going for time? Yeah. How things change over time. So Twitter is an interesting example. Twitter started very small, like most things, and then exploded. But also you see like different languages and how they change over time. And if you look at a daily thing, so it's already 2 years ago now that I collected tweets for a while and then did some averaging and so. And I just put that up because there's one interesting bit in there which is really amazing. Just the red line if you look at it. This is Japanese. So for some reason, Twitter is really popular in Japan. People seem to use it a lot. And because Japan is very homogeneous, most Japanese-speaking people live in Japan and nowhere else around the world. And so for the Japan curve, you get the very typical picture you get for human activity. There's the morning peak, and there's the evening peak. And there's the big drop, like in the wee hours of the night. Whereas for the other languages, it's not as pronounced. I mean, English has that, but English is this combination of the US and Canada, and then the UK and maybe other English-speaking people in Europe. And I'm not sure if you would be able to find Australia and New Zealand there, probably not enough population. But some of the other languages are much more uniform across, for instance, Spanish. But it's also interesting that Spanish is featuring there. Okay, now I've just tried to convince you that standard machine learning does everything wrong. Funnily enough, it's still quite successful because it has been successful, it has become very popular. So of course you need to ask why and how can that be. And there's a couple of reasons I think. First of all, people are reasonably smart with representing stuff. So if you know that things change over time but in predictable ways, you might just represent your data differently. For instance, you never hear about like the stock market that, say, the Vodafone shares have increased by $4. They tell you it has increased by 2% or dropped by 10%. So it's already a relative measure. And that might be something that works the same now as was working 20 years ago when the absolute value of the Vodafone share might have been, I don't know, a tenth or something like that. But also, and this is probably the more common fact and much more common in practice, and you see that with almost every company using machine learning, is that they regularly retrain. They have to retrain because they notice that their models get worse and worse and worse over time. And it's really just the kind of scale in terms of retraining. Sometimes it's good enough overnight, or maybe even once a month, or maybe you have some triggers that tell you it has to be now. So for instance, overnight fraud detection is a typical thing. The big credit card companies put a lot of pressure on online companies that accept credit cards to filter out bad behavior. Or like there's all these web pages in New Zealand that give you house price estimates like Trade Me and One Roof and HomesCo and so. And they regularly retrain the models every month with the sales start of the month. And more interesting maybe is large scale, what does Facebook do? So they published it last year, so it's probably more or less up to date still. And what you can see is that there's totally different time scales. So for your photos, they do that after a certain number of photos, and it's really fast, takes a few seconds. So this, you could call this is like on demand if you want. But for instance, for language, you can take, for the translation bit, you can take days to train, even though they use GPUs for that. And so they do that weekly or every week. And so you see this, it's a bit frustrating, I would say, that you have to do that. And also there's some issues with that. Like training overnight is okay if you have a night, but what is nighttime on the internet? Retraining from scratch with all the data might be slow and not fast enough. You might not have enough hours in the night to be ready in the morning if you use all the data. So you may have to either use a simpler algorithm or less data, and that may mean that your output is not as good. And also, it might be wasting a lot of energy. If you think about Bitcoin, that was popular like 1 or 2 years ago, people were talking about that they were using enormous amounts of energy to compute that. Now with machine learning, we're in a similar position. No one has noticed yet, but if you would sum up how much GPU are there in the world that are being used for hopefully good things, but not necessarily, and the amount of energy that we use for that. Because if you do these experiments, it doesn't matter how much you put, how much the upfront cost was for your system, the main cost is electricity while you run it. Okay, this is why we think and hope that stream mining, proper stream mining, is a good alternative. And it kind of borrows ideas from a lot of areas, and I've only listed 3 here, and I should go a little bit faster, so I won't go into details. There's 5 different challenges. Everything has to be incremental, has to be fast, has to use little memory. You have to be able to predict at any time, and you have to be able to cope with and adapt to change, because we have these non-stationary data sources. And also, the feedback for training is a bit of an issue. You may not have any feedback, or it might become after some time, but often, to be honest, can't be ignored. And of course, that means that everything will always be an approximation. It will never be perfect, will never be 100% correct, but generally you get some bounds. And there's a lot of systems that are currently being developed, mainly research, open source stuff, and also in R you get stream packages. As far as I know, it's still only clustering, but I may be wrong. I haven't double-checked that, I'm sorry. But also companies are now starting to catch on. So Amazon has published something last year which they call the SageMaker, and that claims to be fully streaming aware. I haven't had a chance to test it yet, so I have to believe it. Yeah. Little plug, so there's 2 main textbooks. One is a little bit old now, and I'm not sure why Joao has never thought about having an updated version. And so last year we published our own book, which we mainly did for teaching, and you don't have to buy it, you can read it online for free. And I'll show you the webpage a little bit later. And now it's time for a little demo, because I also want to show you what it looks like. So let's do that quickly. So when you download more, I should just start it. I don't have enough time for that. And let's remove that. And I'll make that a little bit larger. So it has a similar GUI if you want to use a GUI. And I have to warn you, the GUI is very rough, because this is really a research system currently. And the GUI is more just to help people get into it. And it's not supposed to be really used for serious work. Now, there's a lot of tabs, and currently we do classification, and then I can configure something. So evaluation is a big issue with streams. You can't do standard cross validation. So the simple thing is to use data that comes in for testing first, and only afterwards for training. That's called evaluate sequential here, and we have a simple algorithm, naive Bayes, and we have some data sets. So actually I don't have a proper stream. I've just captured some data from a stream in a certain format that's the same as Weka uses, the R file format, and I'm just going to start this here. So we'll learn a naive Bayes classifier, and this is a small data set, only 50,000 examples. It's low dimensional, 8 features, so it was really fast. I already finished here. There's a lot of textual output here, and I'll just the main thing for that is that you can download it and use it later, and I'll show you that in a minute. And down here we had some output, and you see that the defaults are such that usually you have more than 50,000. But this is just the accuracy curve. So you see a learning curve over time, which is quite useful usually. Because what you see is that, yeah, it's a reasonable accuracy, and there's some dips here, and there's some problems, but it seems to be able to recover, even though we've done nothing special. Now, we can, of course, play around with a lot of algorithms here. There's only a few that I wanted to quickly show you. There's one thing, which is, if you know about time series, which I'm sure some or many of you will do, is time series have this phenomenon called autocorrelation, or can have it, usually have it, I would say. If something is strongly autocorrelated to itself, then just predicting the previous value that you've seen is often a good idea. This is what this so-called no-change classifier does. So if there's a classification setting with just 2 class labels, we'll just always predict the class label that we've just seen for the example before. And what we see, what we will see if we start it in this example is, if I also bring up the other one. So the blue line is the one that just predicts the label we've seen before. Very simple, naive, no learning. It's actually really good here, because this is a data set that has enormous autocorrelation. It's about electricity demand going up or down in the next half an hour in the Australian market. Now, there's a lot of, how much time do I have? There's a lot of methods built in, way too many, and some of them are smart and can deal with these problems and can deal with changes and are much smarter. Don't have enough time to show you that here, but I'll show you a summary slide in a minute. And while I'm outside PowerPoint, I wanted to quickly show you this here. This one. Now, R and Python have this really big advantage of having notebooks, or that you can use Jupyter notebooks. But nowadays, you can also use Java and other languages inside Jupyter notebooks. And so on our webpage, we have a simple example showing people how you can actually use MOA and probably all kind of Java code, including Weka, in notebooks as well. So, and you can get like your sequential evaluation curve, or you could get the same low-level numeric output and capture that and process it later. Okay, now back to the slides, because I need to rush it up a bit. Sorry, I'm a lecturer. I can go on forever, so I always have too many slides. Okay. So here's a couple of algorithms. And the top one, the light blue, is online adaptive random forest that kind of wins here. And the next line, the brown line, is this no change classifier. And everything else is like a little bit worse. And there's this big dip around 20 or 20,000 examples in this case. And when you see that, and you only see that if you are able to plot learning curves like that, you would not be able to do that with Weka. You would only see a final result with Weka. You would see that a random forest wins, but you wouldn't know about the dip, for instance. Now, if you see the dip, you want to explore the data. And the explanation is that this was Australia a long time ago, and New South Wales was always part of the market, and Victoria only entered after a while. And the dip is exactly at the point where suddenly you have proper data for Victoria. So the model initially was trained on data that did not include Victoria. And then you have Victoria, and that changes what's happening, and therefore you need to adapt your model a little bit. Okay, so what's missing? There's a lot missing, which is good, because it means we can do a lot of research. So we don't have the deep learning and the really fancy gradient boosting yet. And we have done some initial experiments, so we think we can do it. But currently this is all in Python, but there's hope, because there's this really good PhD student from Mexico, Jacob Montiel, who's just defending a thesis this week in Paris, and we will probably hire him as a postdoc. He started like a MOA in Python, so maybe it's going to be very easy to do that in Python. Now, the other issues that are there is, I said everything is data streams, but actually me being allowed to collect it and be able to access it is not that easy, because usually companies own that, or there are lots of rules around privacy and so. So actually, often what we do is we either just scrape some web sources, like this is a proper satellite image with the green outline, and the other one is the predicted one for the same time step. You see, it's okay. It's not perfect. It's a bit too mushy, but it's getting there. Or we use generators to artificially generate data. That is interesting, but has issues as well. And pre-processing, well, this is one of the dirty secrets of machine learning, is that everyone works and cares about the algorithms, but often they don't matter. It's the pre-processing that makes all the difference. And of course, the pre-processing here also has to be online and incremental, and being able to predict any time and use little memory and time. And so, hasn't seen much research, but there's some happening now. A little bit of that I'm involved with some Brazilian PhD students, interesting enough, which is a really good collaboration. Then the labeling I mentioned before, often the labels are delayed. So if I predict electricity demand for the next hour, after the hour I know what it really was. So it means I have to wait for an hour. Or I may not be able to get information at all unless I do something specific and expensive, like labeling tweets for their polarity. Or, for instance, if I want to know how long a car battery lasts, I can do some destructive testing with some small samples, but I can't do that with every battery because I want to sell them. Even though these days, maybe at the end of life, you might get a message from the battery via the internet if it's connected to the IoT, and so on and so forth. So it's a bit of an issue. Active learning seems to be an interesting avenue to actually deal with that. Now, change management is also interesting, because when I was talking about change and stuff like that, all our current systems are really what you would probably say reactive. They kind of explicitly or implicitly notice that something has changed and do something immediately, but they're not really smart in terms of higher level reasoning about it. And there's some kind of activity in that area. Interesting enough that is often coming here out of Auckland. So there's a very good PhD thesis that has been submitted here 2 or 3 years ago by David Wang or Russell Pierce at AUT. Also there's some interesting stuff about recurrent concepts. But I think there's a lot of options there. And yeah, fertile ground for work. And so for the future, I think what I would like to see is that stream mining becomes mainstream. Currently it's still niche. And I think if we can fill in most of the research gaps, we will be mainstream in, say, 3 or 5 years. In terms of software development, I think it's really exciting times. There's all these cool new languages, like Julia, Rust, Kotlin. There's all these opportunities with working with GPUs, like PyTorch, which is really NumPy for the GPU, if you know what NumPy is. But we also need better tools for understanding and debugging models, and I think some of the future talks will talk about algorithmic fairness and needing to be able to understand what models do. But generally also, most of our code is rough because it's research students and everyone has some time pressure. The exception being this Adam system, because this is someone who knows about software engineering and has the time to do it properly. But I think what we really need for successful and good deployment is not just the open source software that we supply, but also open data, and then the models that have been generated should also be open for inspection to everyone. And with that, I want to conclude, and this is all the current members of the machine learning group, plus a list of current and former research students. And of course, everything I showed you here is mainly these guys' work. It's not a single person, but some of them are more important than others in terms of what they've contributed in terms of code. But generally, it's really good to have them all. And thank you very much.
Any questions?
How big are your streams of data?
Yeah, that's a very good, so if I repeat the question was how big are the streams that we are processing? Already Richard, for his PhD thesis 10 years ago roughly, was using streams of up to 1 billion instances, but that's the caveat, they were really low dimensional. So they were usually like in the tens of features. Then maybe 5 years ago, we were, for instance, processing tweet streams where we would process like 100 million tweets with much higher dimensions because the way you represented the words back then, where we didn't know about word embeddings. Nowadays, I think we would use word embeddings, but that means we would have like 10,000 or 100,000 sparse dimensions. And to be honest, I don't know what the current limit would be. I think it comes back to the algorithm that you use. If you use something very simple, like maybe multinomial naive Bayes for a text problem, then you can probably do huge amounts. If you have some more involved processing, and I wasn't able to show you that, but in this example that we looked at, there was, well, I would claim what you saw was pretty fast. If I had also shown you the adaptive random forest in action, that would have been a lot slower. But at least this tool, even the interface, is multi-threaded as well. So again, I didn't have a chance to show you that, but I can run 8 things in parallel there, even on my little laptop here. And I think that's one of the nice things about the Java environment is, and it's probably one of the reasons why it will still be around for a long time, that you have this really large infrastructure in the cloud where people use Spark or similar setups to process large amounts of data in parallel. And Moa itself is, there's a variant of Moa that's called SAMOA, the Scalable Adaptive Moa, which really targets distributed cloud infrastructure and sits on various different backends that you can choose, like the Storm and there's S3 and so. This is like middleware between the cluster Spark Hub setup and also Spark themselves. They are working. There was a system called Flink, which was done in Germany at the Technical University in Berlin. And that was supposed to go into Spark and the Apache Foundation, but now they have started something similar themselves that is fully incremental. If you use Spark, even Spark can do incremental processing in a batch incremental way. So I think the practical limit at the end of the day is mainly the algorithms that you use.
It's not pure, you don't have space to store your computers.
Yeah. Yeah, so that's the other thing. I mean, the way we work, as long as your input comes in and you can process that in real time, it doesn't matter. And this initial deep learning experiments that I've done, we were using some standard benchmark data sets like CFAR10, and we were using, so this is like 50,000 examples, but we used data augmentation where you corrupt images, and so we generated there was 5 million examples, and that was processed in a few hours, basically. But in this case, it's really just the GPU that makes the difference. And if you have a better GPU or run, like, if you Google and run 1,000 in parallel, you're probably done in 5 minutes. It's a bit frustrating from my point of view that these days, it's almost like back in the days when I was at CERN. CERN was brilliant because they had the infrastructure. And then you go back to the university and you have your single time-shared computer back then. And nowadays at the university, we have some clusters and things available. And we have a nice little farm with like 15 machines that are all 64 gig memory and quad core and all have GPUs now. And some of the GPUs are high-end GPUs that we were lucky to get donated from NVIDIA, but some we bought themselves, standard gaming GPUs, 1080 Ti's or whatever. So you can do something, but large scale you have to, again, go to the big companies these days, like Google or Amazon or Facebook. So if you're a student and can do an internship with them, go for it, do it. You will love it. My son did it, he really enjoyed it. I envy him. Okay.
So, Bernhard, I know it's not really your baby, but Weka's been around about the same length of time that R has been. And someone named Ross might once have described the infrastructure of R as a towering pile of shit. So I wondered if you could comment on how you might have dealt with infrastructure choices that were made early on.
Yeah, to follow up on this interesting comment, I was using a particular Weka class for years in a software engineering course as an example of what not to do. It had one method with 2,000 lines of code. And it was so central and important that no one dared to touch it, because you would break it whatever you do. Then eventually, after a few years, actually Mark Hall was brave enough, after writing a lot of tests, a lot of unit tests to capture what the system currently does and should do after changes. It has improved. There's still one method, I think, with 800 lines of code, which is still bad, but at least it's not as bad. It's a little bit more modular. Yeah, I think this is whatever you build, and I see that with my own code, you start out simple and the first version is easy to understand, and then you add and add and add, and then it becomes a pile of shit. And if you have the time, or if you're lucky to have someone that you can pay to do it, then you might be able to restructure it, or you might be able to, with what you've learned, start from scratch and do things differently. Also, tools change over time. So for instance, the newest Java versions are a lot more flexible, and you can have code in interfaces and stuff like that. So if I would have the time to sit down to redesign, it would look very different. And hopefully, at least the first 5 years, it would be much cleaner.
No more questions? Oh, got a small tip for you.
Oh, right. Thank you very much.
You're welcome.
Oh, wow. Okay, it's a very cool T-shirt with a nice image of New Zealand on the back. I will wear it tomorrow for my lecture. Perfect. Thank you very much.
Now, just don't forget, this is just the first Ihaka lecture. We have 3 more to come in the next 3 weeks, all on Wednesday, same time. Everyone is welcome. Okay, thanks a lot.